Good afternoon, Year 9. We're going to have a look at another short screencast this afternoon. The aim of this screencast is to try to understand together how is it that catalysts are able to have this effect that we can see here. How is it that catalysts can increase the rate of a chemical reaction without themselves getting used up? And we've seen evidence that this is the case from this slide, which we saw in the last screencast together. So, what do catalysts do? Now, as a general sort of statement rather than explanation of how they do it, I suppose, is what's written before you here. They provide an alternative reaction route from the reactants to the product, one that has a lower activation energy than the uncatalyzed reaction. So therefore, less energy is needed for collisions to be successful, meaning that a greater proportion of the collisions will be successful. How do they actually do this, though? There's a statement here, which we're going to explore in a diagram in the next couple of slides. Catalyst provides a surface for the reaction to take place on, provides a surface where the reactant molecules can bind together and react on the surface and then break away from the surface. So this is one way of looking at what's going on. Now, here's an example. Let's move me out of your field of view for a moment. Okay, so here's a simple sort of illustration of those ideas that I've just described to you. So here we are. This, A and CB, these are just two reactants. You can represent them as diagrams, these sort of ball-stick type diagrams, or just by chemical symbols, A and substance CB. Those are the reactants. Now, the product that they're going to convert into is down here. This is A and B bonded together, and C is now on its own. So you can clearly see this represents a balanced equation. We've got a red, a green, and a blue, and down here in the products, a red and a green and a blue. But we've rearranged what's bonded to what. The C and B are no longer bonded together. The A is no longer free. The A and the B are now bound together. That's all the chemical reaction is, a rearrangement of which atom is bonded to which, and that's why they must balance. Now, we've got two routes illustrated, represented in this diagram. One here is reactants proceeding down this route and then ending up as products. Now, what this represents is the uncatalyzed route. In the absence of a catalyst, the A and the C are going to sort of loosely stick to one another like this. And then there's a sort of a weakening bond here between the C and the B. So we've got this sort of transition state here where the A is partially attached itself to a C, the C to B bond is breaking, and then a further rearrangement is needed in which the A and the B are then going to need to bond together and make C. Now, all of this requires energy. The principal amount of energy, the highest amount of energy, is going to be the energy needed to break the chemical bonds. So in total here, we're going to need to break the bond here between A and C that's forming in the transition state, and we're going to need to break this bond here between C and B. And then a little bit of energy is going to be released, making new bonds. But basically, the bottom line is here, a lot of energy is needed to break bonds. And if it's at a medium temperature, room temperature, not much energy is available. So the reaction tends to proceed slowly. However, if we put a catalyst into the picture, we've now got a different route from reactants to products. We've got from here going to here. And this is the route from reactants to products going around this way in the presence of a catalyst. And it's suggesting here a lower activation energy is required, meaning less energy input is needed to allow the reaction to happen, which means that if less energy is needed for the collisions to be successful, a greater proportion of those collisions are likely to be successful. So more product will be forming at each moment in time. Now, the way it's illustrated in this diagram is you can see that everything is, these little dotted lines here represent that everything is sort of weakly bonding itself to a catalyst surface. This is what it meant in the previous slide by the catalyst provides a surface for the reaction to take place on. So the substances are going to attach themselves to the surface. The chemical reaction, the making and breaking of bonds, will occur on the surface of the catalyst. And then the products, that's represented by this arrow here, the products will be released from the surface of the catalyst, leaving the catalyst to be restored back to what it was. And as you can see, it can be recycled, it can be used again, because it doesn't get used up. Okay. Now, we're going to focus in the next couple of little slides on what it is that's actually happening here on the catalyst surface. So, make sure I go in the right direction. So, what we can see happening here, let's move me out of your way again. What we can see happening here is this bronze-coloured thing here. This represents the solid catalyst that's used in this reaction. A lot of catalysts tend to be metals, particularly transition metals. So that's a fitting colour. Think of this as a metallic solid. This is the catalyst. These things here represent the reactant particles, which could be in a gas state, or they could be in a solution. They could be dissolved in a solvent, but they're free to move around. So what they can do is they can travel towards the surface of the catalyst, and they can attach themselves to the surface of the catalyst. And in the first step, that's what you can see happening here now, the reactants have attached themselves to the surface of the catalyst. Now there is a word that is used for that step, things attaching to a surface. The word that we use is adsorb, spelled A-D-S-O-R-B, adsorb, not to be confused with absorb, A-B-S-O-R-B, which is what a sponge does with water. Adsorb is just when things attach to the surface only. They don't actually go inside the object. So these substances are only adsorbing onto the surface of the catalyst. Okay. Now, whilst attached to the surface, the bonds are able to break more easily than they would if the reactants were in the free state. So in this state here, more energy is needed to break bonds. Once they've adsorbed onto the surface of the catalyst, bonds can break. That's what the little flash here is representing. Bonds can break more easily. Less energy is needed to break bonds. And if less energy is needed, that means more particles are likely to have enough energy to break their bonds and successfully react to make product. The next little flash here, this represents product bonds forming. So all of this, bonds breaking, bonds forming, all of this is happening still whilst the particles are attached to the surface of the catalyst. Okay. Final step is the particles can then detach themselves from the surface of the catalyst, meaning the catalyst is now restored back to what it was and can be used again. Remember, catalysts don't get used up. The product detaching, the word we use for that step is the opposite of adsorb is desorb. So the product particles are desorbing from the surface of the catalyst. Okay, so the reaction is occurring more easily, if you like. It can occur more quickly because less energy is required to break bonds whilst substances are interacting with the catalyst, attached to the catalyst. Now, some examples of this where you might meet this type of process. Where shall I put me for this one so I'm not in the way? Let's put me down there. Okay, this is a common example. If you're asked to give an example of where catalysts might be used, this is a motor vehicle engine, like a car engine, if you like. This is the exhaust pipe. A lot of the gases that are produced in the engine of the car, or in some cases it might just be petrol vapor, fuel vapor that didn't get combusted properly, didn't get burned properly, and all of the waste gases, all of these things get pushed out of the exhaust pipe, and then here things pop out into the atmosphere, out of the back end of the car. Now, potentially we've got things like unreacted fuel. We might have poisonous gases like carbon monoxide from the incomplete combustion of hydrocarbon fuels. And we might also have things like nitrous oxides, which are also harmful to us and harmful to the atmosphere. So there's a number of harmful things that could be coming out of the end of a car into our atmosphere. The job of a catalytic converter is to very quickly change those gases into something less harmful to be released into the atmosphere. I say less harmful because, for example, carbon monoxide, which is toxic to humans, will be changed into carbon dioxide quickly before it's released into the atmosphere. That is perfectly safe to breathe, but it's a greenhouse gas. So it's less harmful to us, but it's actually not good for the environment and us in the long run. But anyway, the point is these reactions have to happen very quickly because the gases passing through the tailpipe here are going very, very quickly from the engine. So they've got, a fraction of a second to pass through this chamber here, which contains catalysts, and they have to allow the reaction to occur almost instantaneously, very, very fast indeed. You can sort of see from the structure of this catalytic converter here, inside it, it's like a honeycomb structure, a sort of sponge-like structure. That has a very large surface area. And as you learnt about in previous sections of the course, a bigger surface area leads to a greater rate of reaction. And also because it's a honeycomb structure, the gases are forced to pass through it. They will inevitably be touching multiple places in the catalyst as they pass through it. And that ensures that they should have reacted before they're released. Typically, the sorts of things that are found inside here will be a mixture of metals, and I mentioned already transition metals. A mixture of metals, you may know what word we use for a mixture of metals. They're called alloys, and the alloy, not alloy, the alloys that are used in here is typically a mixture of something like palladium, platinum, and rhodium, something like that. So quite expensive metals as a one-off cost, but then the metals are not used up. So that's okay. Now, another example, just to mention, of catalytic action, let's move me up to the top for this one, is this type of idea. There are catalysts which speed up the chemical reactions which take place inside our body. We call these substances that help the reactions to take place, help them to take place quickly and efficiently. We call these substances enzymes. And it's a similar sort of idea to chemicals acting on the surface of a catalyst. Here we have a substrate. In chemistry language, we would call that a reactant. And over here, we have a product. And in a similar way to the previous slides, there's a sort of an intermediate step, which we would call an enzyme substrate complex. It's where the enzyme and the catalyst have stuck themselves together, and then afterwards they will separate to release the enzyme or catalyst, and then the product is released. So here, enzyme is a catalyst, a biological catalyst. Substrate is a reactant, something in your body which needs to be converted to something else. And then the enzyme, being a catalyst, as you can see over on the product side, is released. It didn't get used up overall. The enzyme has a particular shape, and that's what this lock and key idea is all about. So it will only attach itself to a specific type of reactant, or substrate as it's called in biological terms, one that has the complementary shape, so they can lock and key, they can bind themselves together. Okay, the only other difference to mention about those, I suppose, is enzymes are often made of proteins, and they're quite sensitive to temperature. If they get too hot, they might become damaged, their shape might change, and they might no longer become effective. So these things are a little bit more fragile than the transition metal catalysts that we use in industry. Anyway, that's all for today, folks. I hope that was useful. If I went too fast, please feel free to rewind it, watch it again, etc., as you like. Okay, thanks for listening, folks. Goodbye.